Hello, it's time to play some dominoes. Let's try pips on easy mode first. Okay, we've got a 5-sized equivalence region with sixes, and we need greater than 3 and less than 3. I mean, I think the greater than 3, well, oh no, sorry. Yeah, we need a greater than 3 and a less than 3. So less than 3 could be a 0. That's the only less than 3 we have, in fact. We've got a double 6 there. Greater than 3 will be a 4, and then the other 6 just goes here. Okay, there we go. I had a moment where I was just sort of slightly mixed up by the less than greater than, which just seems to happen. But anyway, there we go. All right, we'll go to the medium. Let's try this. Okay, we have a 15, which could be 3 5s. It could be 2 5s and a 3. It couldn't be because we don't have, sorry, I meant 2 6s and a 3. We don't have, but we don't have a 3, so it's irrelevant. So it could be 1 6, a 5, and a 4. That's conceivable. But anyway, I see something more direct than that. This double 0 must go here because a 1 really can only be made up of a 1 and a 0. So we need that 0, which means now we need a 1 pointing up into the 10. So we could have a 6, a 1 6 pointing up, or a 1 5 pointing up. And that would lead us to either a 4 or a 5 up there. And one of our 6s is spoken for. So is it possible to make the 15 with all 5s? I think it is, because we could put a 6 and a 5 going across here, and then 2 5s here. Does that ruin anything? If we did that, we would need to make the 10 with 6 and 4. That is looking plausible to me. So what were our other 15 possibilities? If we don't use 3 5s, we can't use 2 6s. We can use 1 6 and a 5 and a 4. I think that's the only other possibility. Does that one work? That might work as well. Actually, it might not. I think that actually doesn't work. Because to get the 6 in there, yeah, we'd need here. Then the only other 6 would be the one connected to this 1. That actually doesn't work. So I think we need 3 5s in the 15, actually. So that's helpful to know. Let's see. So how does that interact with this 6 here? So we could have a 5 going into the 6, or we could have, no, we can't have the 6 1 pointing down, because that would ruin the 9. So the only 6 we can use is this 5. But does it need to be across, or could it be pointing down? If it were pointing down, no, that still doesn't work. Yeah, okay, so it does need to be pointing across, because otherwise we'd break that 9 still. Okay, so that looks correct to me. Now, the 3 must be made up of a 1 and a 2. So this 2 is going to be pointing across somewhere, either into the 9 or the 10. If it's pointing into the 9, we'd need a 5. If it's pointing to the 10, we'd need a 6. Those are both conceivably possible. I bet it'll be into the 10, but let's see. If it's into the 9, we'd need a 5 1 going horizontally, and a 6. No, that doesn't work. Right, because if we put this, this 2 here needs to have a 1 below it. Yeah, I don't think that works. So I think this needs to go here, and then we have a 6 1 going down, a 1 5 into the 9, and a 4 finishing off the 9. Yeah, that was correct. Okay, there we go. So let's try the hard one. I haven't had great success with the hards recently. Okay, so we've got a 22-sized region. How might we construct that? We've got quite a lot of zeros, and none of those can go in the 22, that's for sure. What are the highest dominoes we have? We've got a 10, a total of 10, I mean, here. We'd still need 12 more there, so we'd still need 2 6s. Do we have 3 6s? No, we don't have 3 6s. We only have 2. So we do need to use both of them and 2 5s. 2 5s and 2 6s comprise that 22. That is necessary. And look at all of these two-ish clues we have. We have two twos, and then we have three less than twos, which are ones or zeros. And in fact, oh no, we do have ones. Okay. All right, we have a two down here that's pointing vertically into an equivalence region. That could be zeros. Could it be fours? Don't think so. Oh no, it could be. We do have three fours. Yeah, okay. So for instance, if this went up here, we could have this other four pointing into the less than two, and then a four pointing into the inequivalence region, which, those aren't usually very constrained until the end of them. Okay, so the 22 does need double fives. I mean, it could go here or it could go here. We don't really know yet. So I'll just put it in there to get it out of the way so it's not distracting me down below. And then we need two sixes. So actually, one of those sixes needs to point into one of the two equivalence regions. So we've got a 4 equivalence region and a 3-sized equivalence region. So what can we make from the 4? We could use zeros for the 4. We could use 2s for the 4, but actually we couldn't because 2 of our 2s are spoken for. So we couldn't. So we could use zeros, or I think it must be zeros that go into the equivalence region. The 4-sized one. I think that's right. Yeah, okay. So that makes me think, and how many of those do we have? 1, 2, 3, 4. We have 5 zeros. So we could use one of them for a less than 2. I was wondering if we had to force something up here like that, which we could do that, but we could also have a 0 and a 1 going into the less than 2. How many less than 2s do we have in addition to the 4 zeros? Let's see. So we have 1, 2, 3, 4, 5 zeros plus 6, 7. So we have a total of 7 minus the 4 zeros we need here. So we have 3 more less than 2s. They're all spoken for. Okay, so our zeros and 1s are completely spoken for between the 4-sized equivalent region and the 3 less than 2s. That is true. So we cannot use any more of those for any other purpose. Okay, that's helpful. So what might be the equivalence, the 3-sized equivalence region? We can't use 2s for it because we need 3 of them. Oh no, we only need 2 of them. Oh, but we only have 4. Okay, so we can't do that, sorry. What else do we have 3 of? 4s, I bet it'll be 4s. I don't think we have anything else that fits that. So I think that means 2, 4 must go in here. Oops. 2, 4 must go in here. And then a 4 and one of our less than 2s, which could be a 0 or 1, goes there, but that's the only option, I think. And then our only remaining 4 goes here. That's fine. So now we need something that isn't a 3 coming out of the non-equivalence. That's fine. We'll get there. So of our 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. We have exactly 6 sort of between 0s, 1s, and 2s, and they are all going to go in these 3 regions up in the top right. So I think that means we can kind of put them in whatever order we want up there because they're completely taken up. Oh no, that's not true because some of them point elsewhere. Some of them point, for instance, this 6. So this 6 needs, we need to preserve the 0 from that 6. So it goes that way. That's definitely true. And then that means we need the double 0 here. Okay, that is correct as well. So now we need a 0 and a 1 that goes in here because we need to bridge that. And then that actually forces the last 0, which goes here. So now the last 6 must go here. We've got a 2, which can only fit here. And finally, the inequivalence region finishes in this orientation, so we don't use the 3. There we go. Okay, so I mean, I think that was a reasonably logical solve. I just, I didn't blaze through it exactly, but that was, I felt more confident about that than I did yesterday. All right, well, there we go. Those were the pips. Back tomorrow. Bye for now.